Welcome back, everyone. I'm super excited to be hanging out with you today for another explainer on behalf of Forge College. So, if you've been following along with us in the Ethereum fundamentals track, you know we've been breaking down the entire life cycle of an Ethereum transaction. Well, today we're zooming in on transaction validation rules. You can kind of think of these rules as the ultimate, totally unforgiving VIP bouncer for the Ethereum network. We're going to dive into the incredibly strict entry gates that a transaction absolutely has to pass before it's allowed to do, well, literally anything at all on the blockchain.
But, before we get into all that, let's take a quick breath and pivot. In our previous explainer, we were totally up to our elbows in the somewhat chaotic world of automating advanced Solana CLI workflows. I mean, throwing commands into the terminal, wrangling all those scripts, dealing with rapid-fire outputs. It was a bit of a wild ride, right? Well, it's time to hop back over from that command line jungle and into a highly structured, perfectly orderly environment. Welcome to the Ethereum transaction lifecycle, where everything operates like a hyper-efficient postal sorting facility. So here's our routing manifest for today. We'll start with the network post office. Then we'll look at checking the stamp, the sequence number, paying for postage, the acceptance checklist, and finally, next stop, execution. Let's get right to it. Section 1. The network post office, the mental model.
To really grasp these validation rules without getting immediately bogged down in deep cryptography, I want you to imagine an Ethereum node not as a computer, but as a massive industrial postal sorting facility. In this model, a transaction is just a stamped package with a routing manifest attached. And before a package ever gets opened, which in our case means being executed by the Ethereum virtual machine, it goes through a series of rigid checks. These pre-execution checks are the facility's way of ruthlessly filtering out bad, dangerous, or unpaid packages before wasting even a single millisecond of computational energy on them.
Section 2. Checking the stamp, signature verification. Right, so before a sorting facility does anything with a package, they need to know exactly who is trying to send it. In the Ethereum protocol, checking the stamp is what we call signature verification. The node reconstructs the signed payload, and then it extracts the cryptographic R, S, and V signature values. Using those specific values, it mathematically recovers the public key, which then outputs a canonical 20-byte address. Basically, this maps those raw bytes back to a specific sender. Because think about it, if we don't know the sender, we have absolutely no idea whose account to charge for the postage.
But validity is definitely more than just getting the math right. It's all about context. The node enforces the chainId, which is a standard introduced in EIP 155. Using an invalid chainId is literally like trying to mail a letter in Tokyo using a Canadian postage stamp. It simply won't work on this specific network. The node also enforces a canonical S value, and this is crucial because it prevents signature malleability. You can think of that as rejecting a stamp with forged ambiguous handwriting. Together, these checks make absolutely sure the sender is completely unambiguous.
Section 3. The sequence number, nonce equality.
Okay, so we know exactly who sent the package. Now let's look at how the network handles the order of arrival. In Ethereum, every single package an account sends as a specific order, and this is tracked by a value called the nonce. The sorting facility expects the exact next sequence number from a sender. Say your last package was number 4. Well, the network expects number 5 next. If you try to send a package with nonce 3, it's too low. The node assumes this is a stale duplicate or maybe even a replay attack and just throws it right in the trash. But what if you send package number 7? It's too high. Instead of throwing it out, the node actually places it on a pending mempool shelf to just wait until packages 5 and 6 finally arrive.
Section 4. Paying for postage, intrinsic gas and balance.
All right, so the sender is verified and the sequence is correct. Now, the network handles a ton of packages, but it absolutely guarantees it will never, ever get stiffed on the bill. And it starts with intrinsic gas. This is the minimum baseline gas required before any EVM execution even starts. Think of it as the baseline handling cost based on the physical size and the data payload weight of your package. Heavy packages just cost more to move. If the declared gas limit on your manifest doesn't at least cover this intrinsic cost, yep, the package is immediately tossed out.
And it's not just about declaring a high enough limit on the package. Your account actually has to be able to afford it. Under the post-EIP 1559 rules, the node calculates the maximum possible cost based on your max fee and max priority fee per gas. So here's the absolutely crucial balance check. The sender's account must have a prepaid deposit large enough to cover the actual value inside the package, plus the absolute worst-case scenario postage cost. If you don't have the funds to cover that maximum possible expense, no way, your package is rejected.
Section 5. The acceptance checklist,
deterministic inclusion.
So we've covered the individual rules, right? Let's look at how all these discrete pieces form an unbreakable, fully deterministic chain of events. This master checklist outlines the exact chronological flow. And I really want to emphasize this. The order here is strictly intentional. You absolutely must recover the signature first to identify the sender, because, well, you need their identity to look up their specific account nonce and balance. It flows perfectly. Signature, then nonce equality, then intrinsic gas, then the balance check, all alongside some syntax checks. Every single honest validator on the network runs this exact same checklist. This determinism is exactly what allows the entire global network to reach the exact same conclusion to either accept or reject a transaction without ever needing to trust each other. Pretty cool, right?
Section 6. Next stop. Execution. Post-state prec.
Let's see how all this builds the foundation for actual blockchain activity. If your transaction survived that gauntlet, meaning the stamp is valid, the sequence number is perfect, and you have enough prepaid balance to cover the absolute maximum postage, then congratulations, the pre-execution gates are officially passed, the transaction is accepted. This means it is finally allowed to be opened, processed, and executed by the Ethereum virtual machine. Every single check we just explored happens before a single line of smart contract code is ever executed. And that leaves us with a really provocative question. Once the sorting facility finally opens your valid package, how exactly does it rewrite the rules of the ledger? Like, how does it actually change the state of the network? Well, that is exactly what we'll be uncovering in our next explainer on state transitions and storage updates. Thank you so much for joining me today. I really hope this explainer made the rigid entry gates of the Ethereum network clear, approachable, and easy to understand. As a quick reminder, this explainer was brought to you by Forge College. I highly encourage you to head over to forge.college to continue your Web3 education, access more amazing resources, and just keep building your knowledge. Until next time, stay curious.